The third method we're going to talk about here for finding the Jacobian is the static forces and moments propagation method. Now in this method we start with the last frame, frame n, since we have the defined forces and moments at the end effector, and then we do the propagation backwards towards frame 1. So this is opposite to what we did in the velocity propagation. So let's start here by looking at the general form of having a link and a joint. So here we have link I and link I plus 1. In link I we have attached frame I, x, y, and z. And in link I1 we attached link I plus 1, x, y, and z. And here the distance between I and I plus 1 frames is defined by the position of I plus 1 relative to I, as we see right here. Now we have added here vectors that represents the forces and moments. So if I is a 3×1 vector that includes forces in x, y, z, and these forces are basically the forces exerted on frame I due to frame I minus 1, the previous frame. Okay, and then the moments are the same way. It's a 3×1 vector that represents moments in x and y and z, and these are the moments that are exerted on frame I from the motions in frame I minus 1. Now again we have the same forces and moments here defined in frame I plus 1. So the Fi plus 1 is a 3×1 vector of forces exerted on I plus 1 due to I, and the moments that are exerted on I plus 1 due to I. Of course, when we represent these, if we're looking at the forces of on frame I that are exerted by I plus 1, it's exactly the negative of these forces. And same thing with the moments. All the moments that are exerted on I due to I plus 1 are negative of those that are defined as the moments exerted on I plus 1 due to I. And we're going to see this in the equations once we start generating the equations. So let's start with the static forces first. If we apply static forces at the end effector, which includes forces in x and y and z, so this is a general way of applying forces in the Cartesian space. So this is a vector, that's why you have the transpose here. And this vector is relative to frame n, the end effector. Okay, so if we have this vector as the acting force on frame n, and then we try to look and find the summation of forces and moments to hold the whole arm at static equilibrium. So what are the joint torques needed or the joint forces needed so that the arm would stay in static equilibrium? Okay, so what we need to do is we need to add the summation of forces at a particular frame and equate that to 0. So in this case, summation of forces equals to 0. So I have forces Fii here, Fi relative to I, and then I'm deducting Fi plus 1 relative to I, which is this force, in the negative sign. And the reason for this is, remember, Fi plus 1 are the forces that are exerted on frame I plus 1 due to I. And what I need is the forces exerted on I due to I plus 1. So it's the negative of this. Same magnitude, opposite direction. So that's why we have this in negative, and both of these two have to be equal to 0. Now, remember, when we do the addition here or subtraction, both of the reference frames here have to be the same. So this is reference frame for the first force relative to I, and this is the reference frame of the second force relative to I. Okay, but we always like to keep this force as the force of any frame relative to itself. So if we take this and pre-multiply it by the rotation matrix, we can obtain Fi plus 1, I plus 1. Okay, so what we have here is Fi relative to I equals to rotation matrix I to I plus 1, and that would be multiplied by the force of I plus 1 relative to I plus 1. So if you multiply these two together, we get Fi plus 1 relative to to I. Similar to what we did in static forces, we can do the same thing in static moments. So if we apply a static moment at the end of vector, where that static moment is a vector that includes nx, ny, and nz, and that would be a vector relative to frame n. So what we need to do is we need to find the joint forces and moments required to hold the robotic arm at static equilibrium when we apply this moment at the end of vector. Okay, so to do this, we will have to find the summation of moments about any one of these frames and equate that to 0. So what we're going to do, we're going to do the summation of moments about I. So this is frame I. So we're going to take the summation of moments about frame I and equate that to 0. Now let's look at what are the moments acting on I. The first thing here we have Ni. So this Ni in reference to I is placed right here. Okay. And then we have a moment in I plus 1 reference to I. And again, remember this moment here is the moment acting on I plus 1 due to I. And what I need is I need the moments acting on I due to I plus 1. So what we need to do, we need to reverse the sign of this and make it negative here. So that moment basically is the same magnitude, opposite direction to the moment of I due to I plus 1. Okay, so that's why we put here n of I plus 1 relative to I in the negative sign so that we know this is the opposite of this moment. Okay, so we're done with moments in I, done with moments in I plus 1. Now we look at the forces that are acting on frame I. So the moment due to this force Fi is 0 because the distance from Fi to frame I is 0. It's going straight through the reference frame. And then the moments of Fi plus 1 are acting here on frame I. So this is going to be Fi plus 1 times or crossed with Pi plus 1 relative to I. And that would give me the moment of Fi plus 1 acting on I. Now remember again, Fi plus 1 is the acting force on I due to, acting force of I plus 1 due to I. And what I need is the acting force on I due to I plus 1. So I take this same magnitude and opposite direction, which makes it negative. So I place this here, and this makes my moment due to the force I plus 1 acting on frame I. Again, notice here that all the reference frames are relative to the same frame. So reference frame I here, reference frame I here, and reference frame I here, and reference frame I here. Okay. Now, similar to what we did in the static forces, I always like to have the forces and moments here represented as in reference to the same frame as where they're acting. So this one is already in I relative to I. I don't need to change anything here. Here I have n of I plus 1 relative to I, and I need to convert it into ni plus 1 relative to I plus 1. So if I can pre-multiply this by the rotation matrix, it converts it into ni plus 1 reference to I plus 1. Now when we come about this force here, I have force I plus 1 relative to I, and what I need this to be I plus 1 relative to I plus 1 or I in reference to I. Now if you recall in the previous slide when we did the static forces, we found out that Fi relative to I equals to Fi plus 1 relative to I. So we don't need to pre-multiply this by the rotation matrix, since Fi plus 1 relative to I is the same as Fi in reference to I. I can just replace it and put it in place of this. Now if we do this, we're going to have the moment I reference to I equals to moment I plus 1 reference to I pre-multiplied by the rotation matrix I to I plus 1. So this quantity here gives me back an I plus 1 reference to I. Okay, and then I add this to the cross product of Pi plus 1 reference to I crossed with Fi reference to I. And again, remember this equals to this when we saw this in the static equilibrium of forces in the previous slide. I want to make a side note about cross products, just to brush some information about that. So if we have a u and a v, both of these are vectors, 3 by 1 vectors, and we need to find the cross product for these two. Okay, we can generate this form here where we have I, j, and k in the first row, and then we put the 3 elements for the second row for u, and for v we put it on the third row. So we have u1, u2, u3, and v1, v2, v3. These are the two vectors. Okay, so we take this into 3 steps. The first step is we take the I, and then we cross out the remaining row and column elements for the same I, and that would leave us with ui or u2, u3, v2, and v3. And then minus, again we put this here and we cross out the remaining row and column elements that are in common with j, and that would leave us here u1, u3, v1, v3. And then the third step, we have k, and then we cross out the remaining elements on the same row and column as k, and then we have u1, u2, and v1, v2. Okay, so if we take out all the things that are crossed, we end up with this expression. Okay, and then finally we get the determinant of this, so ut v3 minus u3 v2, and that's in the I direction, and then minus, again, determinant of this is u1 v3, u3 minus u3 v1, and that would be in the j direction, and then for the third term we have u1 v2 minus u2 v1, and that would be in the k direction. Okay, so if you put these in their corresponding spaces, then the cross products for u and v would be, this would be in I, this would be in j, and this would be in k. Okay, another way to find this also is to convert one of the vectors, the first vector, into a matrix, a 3x3 matrix, and then do a dot product with the second vector. So for that we can also use these elements, the 3 elements of the u, to construct this 3x3 matrix. As we can see here, we have u1, u3, and negative u1, negative u3, and then u2 is positive here, negative there. If we multiply this by this vector in a normal fashion, dot product, then we get the same results as what we have here. Now that we found the forces and moments acting on each one of the frames or each one of the joints, we can go ahead and extract from these the forces and moments needed for the joints to keep the arm in static equilibrium. So let's take them one at a time. If we look at revolute joints, the only thing acting on revolute joints that would affect the motor or the torque needed for the revolute joint will be the moments. Forces will not affect the revolute joint power needed for keeping the arm in static equilibrium. So we take only NII. So NII is from the calculations we found earlier. This is a 3x1 vector. If we transpose it, it will give me a 1/3, and I can multiply this by ZII, which is a 3x1, 0, 0, 1. So if I multiply these two, I'm going to get a scalar quantity, just one quantity, which is basically the last element in that vector, in the torque vector. Okay, and this would be basically the torque needed for that particular revolute joint to keep the arm in static equilibrium. Okay, that's a scalar quantity. It's no longer a matrix or a vector. Now we move on to the forces for prismatic joints. Again, prismatic joints can only be affected by forces, so no moments or torques will be affecting prismatic joints. So for that reason, we take the forces that we just found earlier in the calculations, and we take Fi relative to I vector. It's a 3x1 vector. If we transpose it, it becomes 1/3, and we multiply that by a 3x1, 0, 0, 1 z, and that would give me a scalar quantity as well. And this would be basically the very last element in the force vector. And that element is the element that's acting on the z-axis. As we all know, both revolute joints and prismatic joints act on the z-axis. So this one here is acting on the z-axis of the revolute joint, and here it's acting on the z-axis of the prismatic joint, where the motion goes. So it makes sense that we extract only the z component on both of these force and moment vectors. Okay, once we extract these two quantities, we call them tau. So tau basically is refers to the moment or the force, depending on what are we looking at. So if we're looking at the revolute joints, that means tau is a torque. If we're looking at the prismatic joint, that means tau is a force. Okay, and as we mentioned earlier, zii is always 0, 0, and 1. Before talking about the Jacobian, I would like to have some introduction here and define a few terms. The first thing here is the work done in Cartesian space terms is the same as the work done in joint space terms. What this means that for the same amount of motion, the work done using the Cartesian space terms is exactly the same as the work done if we use that same motion and define it through joint space terms. Now we can define the virtual torque in this context as the dot product between the force torque vector and a displacement vector. So force torque vector, for example, can be either the Cartesian force torque at the end effector, and that would be multiplied by displacement at the end effector, or it can be forces and torques from the joints multiplied by displacements of the joints. So we can represent this through the equation here. Forces at the end effector. So this could be a 6x1 Cartesian force moment vector at the end effector, and multiplied by delta x, which can be again a 6x1 Cartesian displacement vector at the end effector. Okay, and that would be equal to tau, which is again 6x1 vector of joint torques. Of course, it can be forces if we are dealing with prismatic joints, and that will be multiplied by delta theta, which is again a 6x1 vector of joint displacements, whether it's a prismatic joint or revolute joint. So this relationship here gives me the equality between having the work or the virtual work represented in the Cartesian space or in the joint space. Now this equation can also be written as transpose of F and transpose of tau. Whether we do the transpose or without the transpose, it gives the same results. Now, since we have the definition of the Jacobian as a relationship between Cartesian velocities and joint velocities, we can also represent these velocities as a rate of change in Cartesian positions and rate of change in joint positions. So it can be x dot equals j theta dot, or it can be delta x equals j delta theta. Okay, so now if we take this and replace dx by j d theta from here, so we're going to take delta x and replace it by what's equivalent to delta x, which is j times d theta, and then we get to this equation here, F transpose, and here instead of delta x we have j delta theta equals to tau transpose times delta theta. Now we can divide both sides by delta theta, so we can get rid of delta theta, and then we end up with F transpose times j equals to tau transpose. Now we can transpose both sides, so if we get the transpose of both sides, and then we can get a direct relationship between the Cartesian forces and moments vector and the joint torques vector at the joint level. So this equation here gives me directly the transpose of the Jacobian, which is a relationship between the forces and moments at the end effector to the torques at the joint level. Now that we extracted all the revolute joint torques and prismatic joint forces, now we can go ahead and try to find the Jacobian out of these quantities. So let's take this again one at a time. This method here, by default, it creates the Jacobian relative to frame n. So if we need to transform this into relative to frame 0, we can later pre-multiply it by the rotation matrix. But for now, this method finds it directly in frame n. So let's start with the linear velocities Jacobian. If we just want to find the Jacobian for linear velocities, then we line up all the torques and forces for each one of the joints. So the torques and forces that we have created from the previous step, we line them up here in one column, and that column will have a dimension of m by 1, where m is the number of joints. So if you have 10 joints, this column would be a 10 by 1, and that would include both revolute and prismatic joint forces and torques. Okay, once we line them up, then here on this side, we can just put the equations for each one of these and then extract, similar to what we did earlier, extract the Jacobian as out of this. So here we're going to have the forces for the linear, since this is only the linear velocities Jacobian, so we're only going to use the forces column here. So this will be fx, fy, and fz in a 3 by 1 column. And then here we will extract out of the equations for each one of these taus, we'll extract the matrix needed for these equations to be true when multiplied by the forces. And we're going to see this in an example. Okay, now once we extract these, then the resultant matrix here that we found will be the transpose of the Jacobian. Again, it will be the transpose. So if we transpose it, we get the Jacobian or the linear Jacobian for this particular problem. Okay, before the transpose, this matrix here that we find will be an m by 3, and then after we transpose it, it will be a 3 by m. Now, if we would like to find the angular velocities Jacobian, again, we use the same quantities for the torques and forces of each one of the joints, same way we did earlier. We line up these equations and then we define them again or redefine them again in that format. But now instead of putting the forces, we put the moments. So this vector will be a 3 by 1 vector that includes the moments of frame n, and that would be a 3 by 1. And then from this we can multiply this by a matrix that would represent the transpose of the angular Jacobian. Again, this would be the transpose, the way we find it, and we're going to see this in an example. But then before the transpose, it will be an m by 3, where m is the number of joints. After we do the transpose, it becomes a 3 by 1. Now, if we want to find the general Jacobian, that means we will just combine these two Jacobians together. So we can just take it from the beginning. We can line these up, and this time we have this vector that includes both forces and moments, and this vector here is 6 by 1 vector that includes both. So that would give us a matrix here that would be of dimension m by 6, and that would represent the transpose of our Jacobian. Now, if we transpose that matrix that we get here, that would give us our Jacobian. And of course, m is the number of joints for all these m quantities.